Hey everyone, hope you're having a great day. So we're going to be talking about motion in this video. Finally, we get things moving. All right, so we're talking about motion in 1D, but all these concepts we're going to be talking about fundamentally apply in 2D as well. It's just, of course, simpler to start in one dimension. All right, so first we're going to talk about a couple different quantities or concepts that they might all sound the same at first when you just say the words, but when we talk about the precise definitions, you're going to see that they're a little bit different, and the differences in the definitions between a few terms are very important. So we're going to be paying close attention to that. So first off, in motion, one of the most important questions to ask is, where is an object? And can you precisely describe where it is? So to do that, we talk about position. And to precisely define it, we need to do four things. First, we need to define a coordinate system, right? Coordinate system is going to tell us which direction is positive, which direction is up, things like this. Then we're going to define a reference point. So the reference point says if we're here, we know what the value of our position is. And so, for instance, most of the time when we're defining a reference point, we're defining the origin. Where does 0 start? Then we specify how far away from the origin we are and in which direction on the coordinate system are we moving away from the origin. Are we ahead of the origin in the positive direction or in the negative direction, right? And so you notice that with these two things together, how far from the origin and which direction, this is the components of a vector, right? But before we say the vector, we need to specify our coordinate system and where on our picture the origin is. So some variables that we'll be using to describe position. Often you'll see x, y, z. Sometimes you'll see the variable r to describe position. And right here, this is a vector that says we're at plus 4.5 meters along the x-axis. But in order to describe that position, we first needed to say, okay, the origin is here, and the coordinate system says the positive axis is going to the right, right? Because we could have just as easily said, if I said, somewhere random on this GoodNotes page, here's the position, right? How do you know what that position is, right? If I said, okay, the origin is here, then this position I wrote here would be, 3 squares away, right? But first you need to define the origin in order to know what to call that position. And you notice it's a little bit arbitrary, right? If I said this is my point, you could define the origin to be anywhere. I could define the origin to be here, in which case in that coordinate system, that same point would be -2 to the left of our origin. So I just wanted to point out that the origin that we choose is a little bit arbitrary. And so a lot of times in problems, we choose an origin point that's really convenient for us. All right, so the next type of quantity we're going to be talking about is displacement. All right, and displacement is the change in position. And so you can think of it as a snapshot in time. Like if your displacement is changing, if initially your position is x naught, we'll say, and that it should still be a vector. If initially your position is x naught, and that position is 4.5 meters, and then your final position, x subscript f, is 7 meters, then the displacement, how far have you moved between those 2 points, would be xf minus x naught, which would be 2.5 meters for this example. So contemplate this idea that position depends on your chosen origin, but displacement does not. So, like we said, if this is xf right there, and this is x naught, we said our origin is here, and that would give us these positions, and subtracting them, we get this displacement. But if our origin was here, let's say, then this would be kind of the initial vector for the initial position, and this would be the vector for the final position, right? Your positions would change, but after you subtracted the two, you would still get a displacement of 2.5 meters. So the displacement really doesn't depend on how you define your origin, which is helpful, and we'll see that. So if you have a series of displacements, the total displacement is really just the sum of those displacements. All right, so for example, let's say our initial position is at 3 meters to the right of our origin point, and at first, our first displacement is 1 to the right. Our next displacement is moving 3 to the left, -3. And then our third displacement is moving 5 to the right. So you can see we're kind of using this tip to tail method that we used to add vectors earlier, starting here, going there, moving here, and then our total displacement, to get that, we just add all of those up. 1 minus 3 plus 5 gives us 3 in this direction, right? +3 is our total displacement. Where have we moved from our original position? What is our change in position from our original position? All right, so next question to contemplate is, in this example, is the total distance, is the total displacement the same as the total distance traveled? And you might be able to see right away that it's going to be a little bit different, right? Because first we moved 1 to the right, 3 to the left, 5 to the right, but in the end our total displacement is only 3. So obviously you might be thinking, okay, the total distance we traveled is in fact different than our total displacement. So in class we're going to talk about what is a formula that we can use to describe the total distance we travel. All right. Next question. So we're talking about displacement, but now we're going to talk about how long did each displacement take. So now we're going to be talking about velocity. So the average velocity is what we're going to talk about first. The average velocity is over a certain time interval we call delta t. And again, we're using this symbol delta, right? This little triangle. And delta means kind of a change in this variable, right? So delta x is a change in position, and delta t is a change in time. Anyways, our average velocity is going to be our change in position, the displacement, over the time interval that it took to have that displacement. All right, so for example, you walk 8 miles in the positive x direction in 4 seconds. That would mean over that time period, your average velocity is 8 meters divided by 4 seconds. So your average velocity is 2 meters per second. Pretty straightforward. Next, you walk 3 meters in the negative x direction over the course of 6 seconds. So now our velocity over this time period is going to be -3 meters divided by 6 seconds. So we're moving backwards by half a meter per second. All right, so hopefully this makes sense. So what if I were to ask you, what is your average velocity over those 10 seconds? And you might be tempted to say, okay, let's just take the average of v1 and v2. but that wouldn't be right because you were traveling at this velocity for 6 seconds and you were traveling at this velocity for 4 seconds. So what you really want to do is say, what is the total displacement at the end of your journey? And you divide that by the total time, 10 seconds, over which it occurred. And so that would be, we walked, our initial displacement, right, was 8 meters. And then our next displacement was minus 3 meters. So in the end, we're about 5 meters away from our initial start point. And over 10 seconds, that means our average velocity was half a meter per second. So this is kind of interesting if you think about it. What the first person did is, if this is our origin, they walked 8 meters this way, and then they walked a little bit back, right, and they ended up here. But what this is asking, what's your average velocity? Because you can imagine someone instead walking at a slower pace over those 10 seconds and finally ending up at the exact same point, right? Instead of one person walking a little bit further and then walking back. But if you wanted to know what is the average velocity that you had to walk with to reach the same point in 10 seconds, that would be it. Okay, but a slightly different question again would be, what is your average speed over those 10 seconds? Because we asked, what is your average velocity? We could also ask, what is your average speed? And you might say, okay, obviously it's the same. It's 0.5 meters per second. But is that right? Think about it. First, we walked 8 meters in 4 seconds at 2 meters per second. And then we walked 3 meters in 6 seconds at negative half a meter per second. So what it would actually be is we would be thinking about, okay, now the direction that we're moving in, left or right, doesn't really matter. That doesn't affect your speed, right? Speed is a scalar, independent of direction. It really is just asking, what's the magnitude of your velocity, right? And so what we would say here is, what's the absolute value of your first displacement, 8 meters, and then you would add what is the absolute value of your next displacement, which would be 3 meters, right? Because it doesn't matter that we're going backwards. And then it would divide that by 10 seconds. All right, so our average our average speed is actually going to be around 1.1 meters per second. Right, so you can see that's quite different than the average velocity. This is kind of asking, how hard was the person working in order to actually cover the displacements described, right? Versus the average, it was asking, if there's going to be a smarter person who wants to reach the same point but travel a shorter total distance. This is what they can move at. All right, so that's kind of a drawn out example of the differences between average speed and average velocity, but hopefully that's helpful to you. Next, we're going to talk about instantaneous velocity. All right, now we're going to be doing a little bit of calculus, but don't be afraid. It's just a nice, simple derivative. So the instantaneous velocity is to say what at a specific point in time, what is the current velocity? And we'll illustrate this example graphically in just a minute. But for instance, this is kind of similar to the average velocity, right? What is the change in position over time? except here we're asking if the limit of the instantaneous velocity is kind of like the limit of the average velocity as this delta t, this change in time, gets very, very, very small. So infinitesimally small. So that's why we write dt instead of delta t. So, dt is kind of like much, much smaller than delta t, as small as you can get, right? Take your fingers, if you're, measure between your finger and your thumb, and that's delta t, and then if you kind of just shrink the size of your finger and your thumb so that they're basically almost touching, that's delta t, just a very, very small measure of time. All right, and that's asking how does the position change over that infinitesimally small measure of time. Will give you your instantaneous velocity. So this is kind of the definition of a derivative. How does a function change over an infinitesimally small chunk? And we're taking the derivative with respect to time. So to graphically illustrate the difference between the average velocity and the instantaneous velocity, we kind of have a graph of position over time here, right? Position is going to be on the x-axis, the vertical axis here, which we say is x, which might be a little confusing. And time is on the horizontal axis. So we wanted to know, let's say, what's the average velocity between time 1 and time 2. Right? Well, we would take the position, the difference in position between time 1 and time 2, and we would subtract that to get the displacement, and then we would divide that by the change in time between t2 and t1. Okay, and then the slope of this line gives you the average velocity. But if we wanted to know at time 3, at exactly time 3, what is the instantaneous velocity, what we would do is we would take a line and we would draw a line so that it is perfectly tangent to this position curve. And tangent means it's touching at exactly one point, right? And it's perpendicular to the line at the point it's touching. And that would give us the instantaneous velocity at that point. And so if you could see, this is the average velocity between t1 and t2, but if you were to take the instantaneous velocity at various points, you would get a different answer than the average velocity, right? Because the velocity is kind of evolving gradually in between that time period. All right, so the next question we have to ask is, what if velocity isn't constant? Which is going to be the case quite often, because velocity being constant it's kind of simple. We're going to see velocity changing, and so we're going to be talking about acceleration. A lot of people hear the word acceleration and they assume that means you're speeding up, but acceleration just means the rate of change of velocity. So a negative acceleration, for instance, would mean you're slowing down, and it's still an acceleration. All right, so average acceleration is defined as what is the change in velocity over some delta t, right? And to get that, you would take the velocity at time 2, subtract the velocity at time 1, and then subtract the change in time, divide by the change in time. And acceleration is also a vector. Similarly, we can think about the instantaneous acceleration and take the derivative of the velocity as a function of time. All right, so one super important point I wanted to make is that the acceleration vector and the velocity vector, they don't have to point in the same direction. So what does that mean? That means, let's say your velocity is 4 meters per second and your acceleration is, let's say you're you're walking at a speed, or you're running at a speed of 6 meters per second, and over 2 seconds you slow down to 4 meters per second. Okay, so your final velocity is still positive. You're moving to the right at 4 meters per second, but your acceleration, you're going to take the velocity at time 2 minus the velocity at time 1, divide by the time interval, and you're going to see that your acceleration is -1 meters per second squared. So meters per second squared, those are going to be the units that we're going to be seeing for acceleration. That means every second you're reducing your velocity by 1 meter per second. All right, so you can see that even though your velocity vector is positive, your acceleration vector is negative, right? Your acceleration and your velocity in this example are moving in opposite directions. All right, so here's an example of how we can look at a velocity plot, and then we can draw a corresponding acceleration plot. So in this plot, we kind of have velocity on the vertical axis and time on the horizontal axis. And here we initially have a velocity of 0, and then our velocity decreases, and then the velocity here stays the same over this time period between 2 and 4 seconds. So what can we say about the acceleration? So you can see velocity here is decreasing, which means our acceleration is going to be negative. So initially we have an acceleration of -1. And here our velocity is staying the same, which means over this time period we're going to have an acceleration of 0. So if we're not accelerating, our velocity is staying the same. And then we see the slope of this line is pretty steep, right? And it's actually going up the velocity is going up by 2 meters per second every second, right? That's the slope. It goes up by 2 over a distance of 1 second, which means our acceleration is 2 meters per second squared. All right, and here our velocity is still increasing here, so we're still accelerating and increasing our velocity. But this time we're only increasing our velocity by 1 meter per second over 2 seconds. So rise over run. So our acceleration here is only about 1/2 meter per second squared. And then we hit the brakes, and our velocity starts going in the opposite direction, and we're going down by 3 every second. So our acceleration here is -3 meters per second squared. And then we kind of flatline again, and our acceleration is 0. All right, so hopefully this helps you kind of see the relationship between velocity and acceleration kind of play out in a plot. And this is something we'll be practicing in class. So thanks for watching, and see you soon.